Okay, so we are going to finish up 11.4. So remember, we have been talking about limits and how we can use the limit to find something called the derivative. And that's something that we find a lot in calculus. And so today we're talking about limits. What happens when we have limits of sequences or rational functions, and also talking about limits that go off to infinity. So I wrote these crazy looking rules here on the left-hand side, but what we're going to start with is we're going to start talking about rational functions. So the limits of rational functions. So you can see 10 through 24 here are rational functions, right? It's a ratio of two different functions to each other. And the rules when we take the limit of rational functions look like this. They should look a lot prettier than this, but this is what you got for the last class before school. So basically it's this. If you look at your rational function, okay, and the if you look at your rational function and the degree of the denominator is bigger than the degree of the numerator, then the limit is always going to be 0. Okay, so I can look at this so by degree, I'm looking at the exponent on my variable. Okay, so in number 10, we have basically x to the 0 power over x to the first power. So my denominator is bigger, so the limit is always going to be 0. Okay, if you have a rational function and the degree of the numerator, that's what this is supposed to say. If the degree of the numerator is bigger than the denominator, then the limit does not exist. Okay, and if they're equal, then it's actually just going to be a ratio of the coefficients of the degree of the function. So we'll do a couple of these, but you'll kind of see this pattern is going to work its way out every single time. Okay, and so what we're talking about again is why this section is different than other sections is that we're taking the limit as we approach infinity. So as we get to an infinitely large number, what happens to our rational function? Okay, so I think the first rule and number 10 are kind of the easiest to understand. So what is the limit as x approaches infinity of 5 divided by 2x? So this is a case where the denominator has a higher degree, right? We have x in the denominator and we don't have any number in the numerator. So you can see if we put a gigantic number in for x, we're going to infinity, but if you put in, even 1,000,000, 5 divided by 1,000,000 is going to be, probably if you evaluate on your calculator, it's probably going to give you 0, but it's going to give you, 0.000001. So this is, I think, kind of intuitive for us. If you think about the graph of it too, as our number in the denominator gets bigger and bigger, the limit is going to approach 0. It's actually a nice 0, so that's good. So that one's pretty easy to identify. That's also the only example that I have that the denominator is bigger than the numerator. So if we switch to something like, where are we at? Desmos. Just to kind of show you visually what that looks like. Maybe. Desmos is like, it's the end of the school year. I'm done. Come on, you can do it. Maybe. Oh, I was joking with you, Desmos, and you really did give up on me. Let's see, online graphing calculator. Maybe Desmos is having, let's figure out if it's Desmos or my computer. Oh yeah, I know Desmos. But Desmos is not behaving right now. I know. I think it's my computer because look at it, it's just churning. I've stressed my computer out. All right, well, I am going to pull up my graphing calculator and I'm going to graph 5 divided by 2x. So if you have your graphing tool, or maybe Desmos is behaving for you, you will see that if you graph it, that means you get to see me graph it. You'll get a graph that looks like this. Oh man, see, this is why you don't want me graphing. Okay, use my finger. Very, very highly scientific graph, right? It's going to look like this, but as as x approaches infinity, you approach 0. Now, just a reminder that because it just says infinity, we're assuming that they're talking about positive infinity here. If they are talking negative infinity, which you can see number 14 has a negative sign, 16 has a negative sign, then we're talking about if we approach the left-hand side of the graph. Okay, so that's a pretty easy one. Even if you put in x over x squared, right? The limit is still, or x squared plus 1. If you put that into your calculator, the limit is still going to be 0 because the degree in the denominator is bigger than the degree in the numerator. Okay. All right, so let's skip, oh no, let's do number 12. Okay. So what do you notice about 12? We have the limit as x approaches infinity of 2 minus 7x over 2 plus 3x. Okay, so this is one where the degrees of our degrees of our variables, right, are the same. We have a first degree in the numerator and a first degree in the denominator. So when we have that, it's actually, the limit actually is going to be the ratio of the coefficients that belong to our first degree function. Okay, so what I mean by that is that we're going to take the coefficient that's in front of x, which happens to be -7. Trying to write nicely, I promise. -7. And the ratio that is in front of our variable in the denominator is 3. So the limit of 2 minus 7x over 2 plus 3x is actually -7/3. And that's because the degree of my numerator is the same as the degree of the denominator. So if you graph it, let's see, we'll give Desmos one more chance. Nope. Still doesn't want to do it. Okay. So if you graph number 12, you go old school and you guys can graph on your own, right? If you graph number 12, you actually get a graph that looks a whole lot like the graph of number 10, except the asymptote is actually, if I draw it right, the asymptote is actually at -7/3. So now that I'm saying this, the asymptote and all this, does this look, are you guys having a little bit of a flashback to anything that we did previously? Yeah, a little flashback. Yeah, so this back, I'm trying to remember what chapter it was. It must have been chapter 3 because I don't have my notes in front of me. Yeah, when we were trying to find the asymptotes of the function and we had the rules about the degrees if the degree is higher in the numerator, denominator, or if they're the same. So the rules actually also work for limits. So there you go, full circle. We actually use something again. Oh, can you give me 1 second, please? Sorry. Hello. This is her. Good, how are you? Oh, okay. I okay. Oh, no problem. I will. My dad actually dropped her off, so I'll give him a call and he'll be back over. Okay, great. Thank you so much. All right, bye. Hey, can you tell Poppy to go back and get Ainsley because they're having field day? Yeah. All right. Sounds good. All right. Thanks. Okay. All right. Thanks. Bye. Okay. Sorry, guys. My kids actually take specials at the local school and they got dropped off and they're having field day. So they don't have specials today because they're having field day. Okay. Yeah. So, familiar, I think it's back at chapter 3 when we were learning about rational functions. All of that is back, kind of coming back, right? All right. So we have the case where we have the denominator bigger than the numerator bigger than the denominator. What happens, or no, the same degree. What happens if the degree is bigger in the numerator? Okay. So what happens if, for example, we have number 18? So number 18 is the limit as y approaches infinity of 4y to the 4th power over y squared plus 3. So what happens in that case? The degree of the numerator is bigger than the degree of the denominator, right? So just think about this. What's going to happen is that your numerator, right, is going to increase greater than your denominator is. So your numerator is going to keep getting bigger and bigger and bigger while your denominator is also increasing. So when we talk about something that has a degree that's bigger in the numerator, then the limit actually for this does not exist. Does not exist. And that's just because if you graph this, right? If we look at this again, I don't think Desmos is going to do it for me, but oh, there you are, Desmos. Okay, so if we look, finally decided, if we look at this, 4y to the 4th power divided by y squared plus 3. No, let's actually do x. And maybe, there we go. All right, so if we look at like problem number 18, where our degree of our numerator is bigger than the degree of the denominator, and we're looking out to infinity, our value is just going to keep increasing exponentially, right? It's just going to keep growing and growing. So we cannot find a limit for this particular function. Okay. So yeah, that's pretty much it. It's pretty easy. I'll do one more since those are the only two examples I have where the degrees are different. All the other ones, they actually give you ones that have similar degrees because those are kind of the most interesting one. But for example, if you did number 22, right? Number 22 is the limit as t approaches negative infinity of t squared plus 9t minus 10 over 2 plus 4t minus 3t squared. So the degree of my numerator equals the degree of my denominator, right? And so that means that I'm just going to take the coefficients of my highest degree variable, and that's actually going to be my limit. I'm on the wrong paper, that's why I can't draw on here. Okay, so the coefficients in the numerator in front of t squared is just 1, right? And the coefficient in my denominator is in front of my t squared is -3. So the limit is going to be 1, -1/3. And again, we can graph it if Desmos wants to. So we'll do x squared plus 9x. So x squared plus 9x minus 10 divided by, I have a whole mess going on here. Two x squared plus x. No, I'm reading two different problems. Sorry, guys. That would make for an interesting problem if I just mixed two together. Or wrote the coefficients wrong. Okay. So if we scroll in here, you can see we're looking at the limit as we approach negative infinity, right? And if I pull along my graph here and I move out pretty far, I got to go out pretty far. I still can't get it to get there. I'm eventually going to hit -1/3, right? I'm going to get really close to that when I keep going out. Or you can use the table feature, put in a really big number. That's another option. Okay, so that we should have just done that section when we were doing rational functions, but that's how we find the limits of rational functions. I think it's pretty straightforward, right? Okay, last thing. How do we find the limits of a sequence and if it exists? Okay. So we just spent some time in chapter 8 talking about sequences, right? And there's a couple ways that we can figure out the limits of sequences. One is to first look at the sequence and look if it's starting to diverge or converge on a certain number. Okay. So if it diverges, that means that the numbers are not really consistently moving toward a single number, right? If it converges, then we are pretty confident that we're going to come up with a limit as we approach infinity. Okay, so let me move back here. Get rid of this. Pull up my notes. Last few little questions here. So these are sequences that they give us the definition of the sequence. And it says, write the first 5 terms of the sequence and find the limit of the sequence if it exists. If the limit does not exist, explain why and assume that then n begins with 1. So our sequence begins with 1. All right, so if I look at number 40, for example, Okay, I'm going to do this kind of quickly. If I put in n equals 1, I have 1 over 1 squared plus 1. So I have 1/2 is my first term. When I put in n equals 2, right, I get 2/5. When I put in n equals 3, I get 3/10. N equals 4, I get 4/17. N equals 5, I get 5/26, and so on. Okay, so if I just look at this sequence, okay, again, the degree in the denominator is bigger than the degree in the numerator, right? I notice as my sequence grows, it's growing, right? It's not diverging. It's actually getting the numerator is pretty much staying consistent. It's just moving up by 1, but the denominator is growing at a much faster rate, right? Because we're squaring the number. So eventually, if I get to a really big number, like, and I didn't even type this in, but if I got to, n equals 100, right? I would have 100 over 1 or 10,001 when I get to n equals 100. So what do you notice about these numbers? The numerator is always going to be smaller than the denominator, and the denominator is getting bigger and bigger. So just kind of based off of that, what do you think the limit as n approaches infinity would be? So the limit as n approaches infinity of a sub n, which in number 40, right? 0, right? If we keep getting the denominator is growing so much more than the numerator, when you divide by a really big number, eventually you're going to get to 0. Okay? Cool. All right. What about number, so and you notice that same rules that I had up, right? The degree of the denominator and the degree of the numerator. So what about number 42? We have a sequence where it's defined as 4n minus 1 over n plus 3. So before we even look at the sequence, you'll notice that the degree of the numerator and the denominator equal each other. Okay? So just keep that in mind. If I want to write the first 5 terms in the sequence, I'm basically going to plug it in, right? When n equals 1, my sequence is 3/4. When n equals 2, my value is 7/5, 11/6, 15/17, or 15 out of 7, 18 out of 8, and so on. Okay, so this sequence, when you look at it, it's not diverging. It's not like going from negative to positive to negative to positive. It does follow a pattern. It's not the similar pattern to the problem above because the numerator is actually growing faster than the denominator. So we don't have that situation going on. So what is the limit as we approach infinity? Well, we can use, again, those same rules that we just did for irrational functions, right? We're going to take the coefficients and of the coefficients of our variables, and that is actually going to be our limit. So the limit as n approaches infinity, sorry for the messy writing, of a sub n, so it's going to be 4 over 1, or 4. And again, this is something you could check by putting in, like, say you want to put in 1,000,000 here, okay? So 4 times 1,000,000 minus 1 divided by 1,000,000 plus 3. So if you think about that, that's basically like 4 million divided by a million, right? We have a -1 and a +3, but once you get to a number that big, those little -1 and +3 kind of cancel each other out. So you get a limit of 4. Okay. And then number 44, we get one of each, right? Number 44, the degree of the numerator is bigger than the degree of the denominator. So what do we know about limits when the degree of the numerator is bigger than the degree of the denominator? They don't exist, right? So for number 44, we're going to guess that they don't exist. Let's see what the first 5 terms are, just so you can kind of see what it looks like. So number 44 is 5/2, 17/4, 37/6, 65/8, 101/10. So you can see what's happening with number 44. Looks similar to 42, but 42 isn't kind of growing by leaps and bounds. 44, the numbers in the numerator are growing way faster than the numbers in the denominator. And eventually, that's going to kind of cancel each other out. So as 44, goes to infinity, the limit's not going to exist because the sequence is just going to keep growing and growing. So we would say this does not exist. All right. So that is finding limits when they hit infinity. And that actually completes our chapter 11, completes our pre-calculus. You guys have now finished pre-calculus. Congratulations. Thank you guys so much. It's been an awesome class. I really appreciate you guys. And we will celebrate on Monday. We will miss you, Sarah. So enjoy your picnic. And that's it. So let me know if you have any questions. Get those last few homework problems done, and you will be done with pre-calc. So thanks, guys, and have a wonderful day and a wonderful weekend, and I'll see you Monday. Thank you. Thank you. And Sarah, I'm sure I'll chat with you sometime.